Section: Introduction. Let's dive into the world of transformer models, specifically focusing on the feedforward layer. This layer is a crucial part of these models, but it's also quite heavy on parameters. As the number of hidden neurons in these layers has grown into the tens of thousands, it's become a target for those looking to speed up large models. Interestingly, in these large networks, only a small fraction of the feedforward hidden neurons actually play a role in determining the output for any single input. This has led to the idea of designing networks that are modular, taking advantage of this fact. Recent work on making feedforward layers more modular has focused on architectural designs that promote sparsity. The common approach is to divide the feedforward layer into separate blocks of neurons, referred to as experts. A gating layer is then trained to decide which combination of experts should be used in the forward pass. The inference process is then sped up by only using the top-scoring K blocks. While this approach does reduce the inference time, it remains linear in relation to the width of the feedforward layer. It also relies heavily on noisy gating for load balancing among the experts, which can complicate training and encourage duplicity. Now, let's introduce the fast feedforward FFF architecture. This is a new approach that accesses blocks of neurons in logarithmic time, rather than linear. The FFF architecture divides the input space into separate regions using a differentiable binary tree. It then learns the boundaries of these regions and the neural blocks assigned to them simultaneously. This is done by executing neurons conditionally based on the tree. A small subset of node neurons is set aside to decide which combinations of leaf neuron blocks should be computed to produce the final output. As training progresses, the region boundaries become more defined, and the mixtures tend to select only one leaf that can be accessed in log time. To put it in simpler terms, let's say we have a learning target function f. The traditional approach is to train a feedforward layer f of width w to approximate f. The mixture of experts, MO, approach, on the other hand, chooses an expert width e that doesn't hinder performance, and then trains separate expert blocks of neurons mixed by the partially randomized output of a gating network of width g. The learning target f is then approximated under the mixture of k best scoring experts. Fast feedforward networks, FFFs, however, take a different approach. They leverage the fact that different regions of the input space activate different sets of neurons in wide networks. FFFs of depth d learn a tree partition of the input space determined by their nodes, and small leaf feedforward networks of width L, which are trained so that each leaf approximates the partial target function f on its respective region. An FFF with depth d and leaf width L can use all 2*d*L hidden neurons to learn f, but only requires one leaf of width L to compute its output for any input, and does so at the lookup overhead of only d neurons. In comparison, the leaves in FFFs are similar to the experts in MOs, but the FFF tree network regionalizes the input space rather than voting on expert prowess. For a feedforward network of width w and a choice of leaf size L, one can choose d equals log 2, seal, with L, and access the leaf in O, d, equals O, log, w, time instead of O, g, equals O, w, time. Interestingly, the FFF approach also represents a differentiable relaxation of the classical notion of KD trees. The process that allows a large feedforward layer to be broken down into a number of smaller leaf layers while maintaining its predictive performance is called hardening. During training, the nodes of FFF perform a soft choice over the outputs of their two children, and based on the final loss incurred, the optimizer updates both the weights of the children and the weights of the parent that computed the choice. During inference, a single hard decision is made at each node depending on the rounding result. Hardening is the process of nodes learning boundaries such that the soft choices they make for individual inputs become more decisive. We've observed that in settings where there's plenty of representation power, i.e., wide leaves and deep FFFs, the hardening process often happens naturally. In settings where more representational power may be needed, this process either happens but stalls prematurely, or happens at a very slow rate. In these cases, we choose to encourage it with the addition of a hardening loss. Thanks to hardening, the performance of the soft training setting carries over to inference. As a bonus, the learned regions can also be used as a partition of the input space for interpretability, surgical model editing, mitigating catastrophic forgetting, reducing replay data budget, and more. Section summary. The fast feedforward FFF architecture is introduced as an alternative to the traditional feedforward FF architecture in transformer models. FFF divides the input space into regions using a differentiable binary tree and simultaneously learns the boundaries of these regions and the neural blocks assigned to them. This approach allows for efficient inference by accessing only a subset of neurons in logarithmic time, while also enabling interpretability and other benefits. Section: User Manual. Let's imagine you have an existing architecture with a feedforward FF layer of width W, and you're considering replacing it with a fast feedforward FFF layer. Here are two scenarios you might encounter. Scenario 1. You're aiming for quicker inference. In this case, you should select a value for L that is less than W and fits within your target inference budget. Then, you can experiment with different depths D that are greater than or equal to the logarithm base 2 of W divided by L. This will help you achieve the performance you're looking for. However, keep in mind that L needs to be large enough to learn the partial function in its region, and the final training width, which is L times 2 raised to the power of D, might end up being larger than W. Scenario 2. You're aiming to partition the input space. Here, you should choose a D, such that 2 raised to the power of D meets your expectations for the number of regions. Then, you can experiment with L that is greater than or equal to W times 2 raised to the power of negative D for optimal performance. Again, L needs to be large enough to learn the partial function in its region. For larger D, you might need to actively counteract the effects of overfragmentation. Now, let's talk about our contributions. 1. We present the fast feedforward FFF architecture, a counterpart to the feedforward FF architecture. The FFF only uses a fraction of its neurons that can be accessed in logarithmic time at any given moment. 2. We explore how leaf size and depth impact the predictive performance of FFFs as standalone models. We find that in sufficiently large settings, FFFs perform comparably to FFs of the same training width but with significantly faster inference. Moreover, FFFs outperform FFs of the same inference size in terms of memorization and generalization. 3. We compare the FFF architecture with the mixture of experts (MO) approach, examining their predictive performance and inference speed as the number of blocks increases. Our experimental results support the claimed benefits of our design. 4. We show that FFFs can feasibly replace FFs in larger, more complex architectures like transformers. Let's now discuss the algorithm. We'll denote the network input and output dimensions as dim_I and dim_O respectively. We'll refer to a feedforward network with A inputs, B neurons, and C outputs as a left less than A, B, right greater than feedforward network. We're simplifying the terminology used for multi-layer networks and only discussing one set of neurons with both input and output weights. For instance, the BERT-based feedforward layer with 768 input dimensions, 3072 hidden neurons, and 768 output neurons would be referred to as a feedforward layer with 3072 neurons, each with 768 inputs and 768 outputs. This makes our explanation much simpler. Section Summary. The paper introduces the fast feedforward FFF architecture as an alternative to the feedforward FF architecture. It explores two cases: 1. Achieving faster inference by choosing an appropriate width and depth, and 2. Partitioning the input space by selecting the depth and width. The FFF architecture demonstrates comparable performance to FF architectures while significantly improving inference speed. It also outperforms FF architectures in terms of memorization and generalization. The paper compares FFF with the mixture of experts (MO) approach and shows the advantages of FFF experimentally. Additionally, it demonstrates the feasibility of using FFFs in larger architectures like transformers. Section: Definition. Let's break down the complex concepts in this paper into simpler terms. We're discussing a type of network called a fast feedforward network. This network has a certain depth, node size, and leaf size. It's made up of two parts: a set of nodes and a set of leaves. The nodes are essentially smaller feedforward networks with an added sigmoidal activation on the output. These nodes are arranged in a balanced binary tree, meaning each node has two children nodes. The leaves, on the other hand, are also smaller feedforward networks. All the weights in this network are trainable, meaning they can be adjusted during the learning process. The network operates using a deterministic algorithm. The nodes are arranged in a tree that makes a soft choice over the leaves in the form of a stochastic vector. During training, the network performs a mixture of experts over all leaves, with the choice weights of the mixture computed by ascending through the tree from the root node. During inference, the decision at each node is taken to be the closer of 0 or 1, and the algorithm proceeds from the root, always choosing only one branch depending on the local node decision. The tree component of the network divides the input space into regions, with each leaf responsible for exactly one region. The boundaries between these regions are determined by the node networks. When the node size is 1 and there is no activation on the node network but the head sigmoid, the boundary is the activation plane of the hidden neuron. The norm of the plane's normal vector, which equals the weights of the neuron, affects how quickly the sigmoid goes from 0 to 1 around the boundary. This determines how clearly the boundary is defined. For the predictive performance of the network to be maintained, one must not lose predictive information when rounding the choice scores. This loss of information is minimal when the boundary decisions have been properly hardened. Hardening at a node generally does not have to involve adjustment to the boundary as a manifold in space. Progressive uniform rescaling of boundary coefficients suffices. Interpreting the node choice scores as Bernoulli probabilities, hardening can be tracked by monitoring the batch mean of entropies of the choices scores at each node. In our experiments, we found that rounding choice pairs with entropies below 0.10 tends to lead to only very modest deviations from the network's performance. For situations where the hardening of node decisions does not occur to a sufficient extent on its own, hardening can be encouraged by the addition of hardening loss. The total loss can be calculated as the sum of the loss due to the outputs of the network and the product of the hardening loss and a training hyperparameter. The hardening loss is the sum of the entropies of the choices scores at each node. Section summary. A fast feedforward network, FFF, is a network with multiple layers and nodes that form a balanced binary tree structure. The nodes in the tree make predictions for different regions of the input space, and the boundaries between these regions are determined by the node networks. Hardening is a process that ensures the predictive information is not lost when rounding the choice scores, and it can be achieved by adjusting the boundary coefficients or adding a hardening loss to the total loss function. Section. Overfragmentation. Let's talk about a phenomenon called overfragmentation. This happens when we allow fast feedforward networks to learn too many hard boundaries. In simple terms, the network starts to divide the input space into too many separate regions. It then tries to learn parts of the learning target in a way that is too specific for each region. This overfragmentation can lead to two main issues: localized overfitting and what we call the shrinking batch problem. Localized overfitting is a process that happens once the model has hardened enough. The boundaries of the regions are no longer flexible, and certain parts of the model learn to overfit the training data on their specific regions. This happens because they stop receiving significant updates from the neighboring regions. However, they may still need to handle test samples that the training data for their region doesn't fully understand. This localized overfitting behaves just like classical overfitting. The performance on the validation set stops improving or even gets worse, while learning on the training set continues. One way to mitigate this is by randomized child transpositions. This means that the decisions at each node can be randomly swapped with a low probability. This exposes their children to the training data of neighboring regions, which can help improve generalization performance. The shrinking batch problem is another issue that arises from the hardening of the leaf region boundaries. This problem occurs when the batch size becomes too small for the partition of the input space learned by the fast feedforward tree. If the partition of the input space is too finely grained and the boundaries hardened, each leaf ends up receiving significant updates from only a small fraction of the training samples. This results in inaccurate progress in gradient descent. This shrinking batch problem can lead to poor learning performance, such as low training set accuracy, early stalling, and chaotic development. However, it can be mitigated with larger batch sizes, gradient accumulation, and smaller learning rates, or more generally with localized optimization. Now, let's talk about the complexity of our algorithms. We measure this in terms of the parameters d, n, and l. In our experiments, we found that n equals 1 was sufficient, but we keep n in for the sake of generality. The training complexity involves a forward pass that ascends through d levels of the tree, passing through node neurons to compute the final choice vector c. This takes time proportional to 2 to the power of d minus 1 times n. Then, the leaf outputs are computed and mixed by c, which takes time proportional to 2 to the power of d times l. This means that the forward pass takes time proportional to 2 to the power of d times l plus n, minus n, and a, d plus 1, step backward pass back to the decision on the root. From an implementation standpoint, we express the ascent through the tree as a single loop making d identical batched computations, and then perform the final leaf forward pass and expert mixture. Section summary. When fast feedforward networks learn too many hard boundaries, it can lead to overfragmentation, where the network divides the input space into exponentially too many disjoint regions. This can result in localized overfitting and the shrinking batch problem, where certain regions overfit the training data and the batch size becomes too small for accurate gradient descent progress. Mitigation strategies include randomized child transpositions and localized optimization. The training complexity of the algorithm is expressed in terms of the parameters d, n, and l, with a time complexity of O, 2D1, n, for the forward pass and O, 2D, l plus n, n, for the backward pass. Section. Inference Complexity. Let's delve into the complexity of inference and the size and width of fast feedforward networks, FFFs. Inference complexity refers to the computational effort required to make predictions using a model. In the case of FFFs, the inference process moves up the tree structure in d steps, each time executing one node network. After this, it performs inference on one leaf, which takes a time proportional to d times the number of nodes n plus the number of leaves l. In terms of how this is implemented, the journey from the root of the tree to the leaves is carried out as a batched computation of a set of weights and biases. This involves multiplying and accumulating these values, comparing the resulting logit to 0, and then advancing the index based on the comparison result. In our experience, when using ahead-of-time compilation for CUDA, the selective indexing of weights for node decisions appeared in the native code as a simple offset in the data load for batched matrix multiplication. This only added a small constant overhead at the hardware level when compared to feedforward layers. Now, let's talk about size and width. FFFs are made up of two types of neurons, node and leaf neurons. To make comparisons easier, we differentiate between network size and width. An FFF with d, n, and l, as defined, has a training size of 2 to the power of d minus 1 times n plus 2 to the power of d times l. These are all the neurons in the network, and they are all affected by optimization. The inference size is dn plus l, as these are the neurons used to produce the inference output. However, only the leaf neurons produce output, with the node neurons solely involved in the computation of the mixture of the outputs of individual leaves. Therefore, we say that the FFF has a training width of 2 to the power of d times l, and an inference width of l. We conducted several experiments to explore the effects of assigning neurons with learnable regions of influence, compare the predictive performance and speed of FFFs to that of mixture of experts, MOs, and assess the feasibility of FFFs as parts of deeper architectures. The task for each experiment was image classification, and we evaluated the classification accuracy in the usual way. To compare the qualities of individual models, we measured 4 quantities. First, we looked at memorization accuracy, which is the ability of the network to learn the training set. A memorization accuracy of 100% means that the network has successfully memorized all the predictions for the training data. Second, we measured generalization accuracy, which is the ability of the network to correctly predict the classes of previously unseen samples in the test set. We also measured inference time and speedup. We ran each model 10,000 times with a batch size of 2048 on a single NVIDIA A100 GPU. We reported the average inference time per single forward pass under repeated trials, along with its standard deviation. We also reported speedup, which is the ratio of the average inference time for the vanilla feedforward network of the same training width to the average inference time for the given FFF model. In simpler terms, speedup tells us how much faster the FFF was than the vanilla feedforward network with the same number of neurons available for making predictions in training. Section summary. The inference complexity of the fast feedforward forest FFF algorithm is determined by the number of steps it takes to ascend through the FFF tree and perform inference on a leaf, resulting in a time complexity of O, dn plus l. The FFF has a training size of 2D1, n plus 2del and an inference size of dn plus l, with the difference between size and width referred to as overhead. Experimental evaluations compare the predictive performance and speed of FFFs to mixture of experts, MOs, and assess the feasibility of FFFs in deeper architectures, measuring memorization accuracy, generalization accuracy, and inference time. Section. Explorative evaluation. We're going to delve into an exploratory evaluation of fast feedforward networks, comparing them to traditional feedforward networks. We're interested in how different parameters affect their predictive performance and speed. We're focusing on 3 main parameters: leaf size, depth, and training width. We want to see how these factors influence the network's ability to memorize and generalize. For each fast feedforward network, we're also looking at a feedforward network with the same training width. We're doing this because only leaf neurons are directly involved in making the classification prediction for the inputs given. We trained fast feedforward networks with various training widths and leaf sizes, using 3 different datasets: USPS, MNIST, and Fashion MNIST. For each combination of width and leaf size, we calculated the depth using a logarithmic formula. We chose these widths intentionally, as any fast feedforward network with these parameters will have an inference width smaller than 16, which is the smallest configuration we used. We also trained a standard feedforward network for each width as a baseline. We fed the networks flattened images and used a batch size of 256 and pure SGD optimization with a learning rate of 0.2, regardless of the size or depth of the networks. However, we did notice that deeper fast feedforward networks benefited from larger batch sizes and smaller learning rates. We used a hardening loss with a scale parameter of 3.0 and ran each configuration 10 times. We're reporting the performance of the best model for each configuration. Our results showed that increasing the width, leaf size while keeping the depth constant all improved memorization and generalization performance. Fast feedforward networks performed comparably to feedforward networks. For larger widths and depths on USPS and MNIST, fast feedforward networks were only slightly worse than vanilla feedforward networks. Interestingly, these were also the configurations where fast feedforward networks showed the most significant speed improvements. On the Fashion MNIST dataset, we saw the same trends, but we needed a larger fast feedforward network to match the performance of the feedforward networks. The inference speed improvement was more significant for wider and deeper networks with a constant leaf size. However, if the training width was kept constant, there was a trade-off between increasing depth, and therefore speed, and performance. We also noticed that networks with large depth and small leaf size showed overfragmentation, leading to a rapid decline in memorization and generalization performance. This was particularly noticeable with greater depths. This can be explained by overfragmentation, as each leaf receives only a few samples per batch on average. In conclusion, our findings suggest that fast feedforward networks can perform comparably to traditional feedforward networks, with the added benefit of improved inference speed. However, careful consideration must be given to the configuration of parameters to avoid performance issues related to overfragmentation. Section Summary. In this section, the authors conduct an explorative evaluation to understand the impact of parameters on the performance and speed of fast feedforward networks compared to traditional feedforward networks. They investigate the relationship between leaf size, depth, and training width, and find that increasing width, leaf size, and keeping depth constant all contribute to improved memorization and generalization performance. Additionally, they observe that wider and deeper networks result in greater speed improvements, but there is a trade-off between depth and performance when the training width is kept constant. Furthermore, decreasing leaf size while increasing depth leads to decreased performance due to overfragmentation. Section TLDR. In a nutshell, fast feedforward networks, FFNs, perform as well as traditional feedforward networks, FFs, of the same training width. They are quicker as the training width increases and, when pushed to their limits, they show a balance between speed and performance, and a tendency towards overfragmentation. Let's delve into the details. We evaluated FFNs of varying depths and leaf sizes in relation to their inference size. We chose inference size as our comparison point with FFs because it directly impacts the computational cost of inference, unlike the inference width. We trained FFNs for various configurations, using different datasets, and calculated the inference size for each. We also trained a standard FF as a baseline for comparison. We kept all parameters the same, except for the hardening loss, which we found to occur naturally, so we didn't enforce it. We ran each configuration 10 times and reported the best results. Our findings were quite diverse due to the many possible combinations of leaf size and depth. As expected, larger depths and leaf sizes resulted in better memorization and generalization performance. Moreover, FFNs outperformed FFs of the same inference size. FFNs of varying depths and sizes consistently outdid FFs with widths equal to the FFN inference sizes, in terms of both memorization and generalization. The difference in memorization was particularly noticeable and increased with depth and leaf size. In terms of generalization, FFNs initially had an advantage over FFs, but eventually, all models' performances converged, reaching the limit of the simple, single-layer feedforward only approach. In summary, FFNs deliver performance more readily than FFs of the same inference width. We also compared FFNs against mixture of expert layers, MOs, and FFs of varying training widths in terms of their predictive performance. We kept the leaf and expert width constant and focused on the architecture's ability to deliver good memorization and generalization properties, as well as the computational resources required to achieve these properties. Section Summary. Fast feed-forward networks, FFFs, perform comparably to regular feed-forward networks, FFs, of the same training width, but are faster as the training width increases. FFFs also exhibit speed-performance trade-offs and overfragmentation when pushed to their limits. In terms of inference size, FFFs outperform FFs of the same size, with larger depth and leaf sizes leading to better memorization and generalization performance. FFFs consistently outperform FFs with widths equal to the FFF inference sizes, but eventually plateau at the limit of the single-layer feed-forward only approach. FFFs are also compared to mixture of expert layers, MOs, and FFs of varying training widths in terms of predictive performance and training compute required. Section: Method. Let's delve into our methodology and subsequent discussion. We conducted our experiments using the unmodified CIFAR10 dataset. We trained various types of networks, including feed-forward, mixture of experts, MO, and fast feed-forward, FFF, networks. We increased the size of these networks while ensuring they maintained the same training width. To keep the inference width consistent, we set the leaf width at 32 and the expert width at 16, always involving two experts. It's important to note that while networks with a single expert can be used for inference, they can't propagate gradients to the gating network. We used widths ranging from 2 to the power of 6 to 2 to the power of 10, which corresponds to MO networks with 16 to 64 experts and FFFs with depths ranging from 1 to 5. To promote equal importance and load balancing in MOs, we set both the importance and load weights at 0.1, following previous research. To encourage FFF hardening, we used a value of 3.0. We trained all models with a batch size of 4096 for up to 7000 epochs, stopping early after 350 epochs if no improvement was seen in the validation accuracies. All models were trained using the Atom optimizer with a learning rate of 0.001, which was halved when the training accuracy plateaued every 250 epochs. Now, let's discuss our findings. The results are presented in the table. Initially, we noticed that the M_A and G_A metrics improved with larger training widths across all models, except for G_A on FFFs, where localized overfitting negatively impacted performance. FFFs were the quickest to deliver M_A and G_A results. However, they provided slightly lower M_A scores than feed-forward networks of the same training width and suffered from localized overfitting as the depth increased. Interestingly, FFFs outperformed MOs of the same training width. They consistently delivered better M_A and G_A scores than the MO networks and did so in less time. We believe this is primarily due to the controlled noise introduced to the expert mixture computation, which helped with load balancing and generalization. Without this noise, MO networks would overfit and learn only with a few experts. We also experimented with different values for the importance and load weights, but found that these generally hindered the load balancing effort. Our final values for batch importance and load were consistent with those found in previous research. Section Summary. In this section, the authors describe their experimental setup and results. They trained different types of networks on the CIFAR10 dataset and found that increasing the training width improved the performance of most models, except for one type of network that suffered from localized overfitting. The fastest network in terms of delivering results was the fast feed-forward network, FFF, which outperformed the mixture of experts, MO, networks in terms of accuracy and efficiency. The authors attribute this difference to the controlled noise introduced in the FFFs to aid load balancing and generalization. Section TLDR. In simpler terms, we're exploring how fast feed-forward networks, FFFs, can provide more efficient data representation than mixtures of experts, MOs, when they have the same training widths. The speed at which these networks process information, or their inference speed, is determined by their gating or lookup mechanism. To understand this better, we kept the width of the expert or leaf network constant and measured the time it took for feed-forward, mixtures of experts, and fast feed-forward networks to process information. We increased the number of experts or leaves in each trial to see how wider networks performed. To make our experiment more realistic, we simulated the conditions of a BERT-based feed-forward layer, where the input and output widths of all neurons were set to 768 each. In our experiment, we considered feed-forward models with widths ranging from 32 times 2 to the power of 1 to 32 times 2 to the power of 5. We highlighted the 32 neuron blocks for easy comparison with other models. We also evaluated mixtures of expert models with expert width E equals 32 and 2 to the power of 1 to 2 to the power of 15 experts, and fast feed-forward models with leaf width E equals 32 and depths 1 to 15. To ensure that the mixture computation didn't affect our measurements, we kept E equal to L and set K to 1, even though this configuration isn't trainable. Each model performed inference on BERT base inputs with a batch size of 256, exactly 20,000 times. Our results showed that both mixtures of experts and fast feedforward networks significantly increased the inference speed compared to the feedforward baseline. However, we noticed that the inference time for mixtures of expert models increased exponentially with the number of experts, while the inference time for fast feedforward models increased linearly. This confirmed our theoretical analysis of the inference time complexity of the two architectures. We also found that fast feedforward networks could replace standard feedforward layers in the transformer architecture, significantly improving its performance. We previously noted that if the leaf sizes are too small for a given problem, it could lead to overfragmentation. So, we pushed our experimental setup to its limit in terms of leaf size and investigated the effect of overfragmentation in a deep transformer. Section summary. Fast feedforward networks, FFFs, provide better representational power than mixture of experts, MOS, networks of equal training widths. The difference in inference speed between the two architectures is solely due to the functioning of the gating, lookup mechanism. Experimental results show that FFFs offer significant acceleration to the inference speed, with a linear relationship between the expert count and inference time, while MOS exhibit an exponential growth in inference time. This confirms that FFFs can be used as layers in the transformer architecture to improve performance. Section. Method. Our approach. We conducted our experiments using the CIFAR10 dataset, which consists of 32 by 32 pixel images with 3 color channels. We applied random horizontal and vertical flipping, as well as random linear transformations such as translation, rotation, and scaling. We utilized 4-layer vision transformers as our models, with a patch size of 4, a hidden dimension of 128, an input dropout rate of 0.1, and no layer dropout. We experimented with vision transformers that had their standard feedforward layers replaced by fast feedforward layers with a training width of 128. We also used a baseline vision transformer with feedforward layers of width 128. The fast feedforward layers had leaf sizes ranging from 1 to 32 and depths calculated as the base 2 logarithm of the ratio of the width to the leaf size. We tested 3 levels of hardening, denoted as h equals 5, 10, and infinity. Here, infinity means that the fast feedforward tree was effectively frozen from the start, meaning the boundaries were not trainable. We used the Atom optimizer with an initial learning rate of 0.0004, which was halved whenever the validation accuracy plateaued over 50 epochs. For each combination of leaf size and depth, we reported the best model's generalization performance and the speed increase at the feedforward layers, not the entire transformer. Our findings. The outcomes of our experiments are presented in the accompanying table. A visual representation of the hardening process across the transformer layers can be found in the appendix's figure. As expected from our algorithm complexity analysis, the speed increase at the feedforward layers grew as the leaf size decreased. We found that even fast feedforward layers with an inference width of 1 were enough for the vision transformer to perform reasonably well, with only a 5.8% decrease in performance. We also noticed that the generalization performance didn't suffer significantly due to the increase in depth and decrease in leaf size. This contrasted with the results in the table, and we believe this is due to the transformer's depth, which is a promising sign for the viability of fast feedforward layers as replacements for feedforward layers. In summary, fast feedforward layers can speed up inference in vision transformers compared to feedforward layers of the same training width, with only a minor decrease in performance. Related research. Our research intersects with efforts in 2 areas of inference acceleration. Section summary. The authors conducted experiments on the CIFAR10 dataset using vision transformers with different configurations. They replaced the feedforward layers with fast feedforward layers of varying leaf sizes and depths. The results showed that even fast feedforward layers with an inference width of 1 can deliver reasonable performance, with only a 5.8% decrease in performance. This suggests that fast feedforward layers can provide inference acceleration in vision transformers with a small trade-off in performance. Section. Conditional execution. Let's delve into the topic of conditional execution and modular, mixture of experts, models. In the past, there were attempts to modify the designs of multilayer perceptron, MLP, and convolutional neural network, CNN, models to allow for partial execution where possible. This was achieved by learning policy distributions or additional controlling neural components to decide which blocks of layer neurons to execute during the forward pass. However, these methods are not as popular today due to a shift away from custom architectures. In contrast, fast feed-forward networks simplify this process. They hide the learning of leaf regions from the user, except for the hyperparameter h if used, and are ready for inference once trained. This means they don't need any adjustments when included as part of transformers. There was also an interesting approach proposed that is similar to deep convolutional neural networks. It learns to route the input through a sequence of chosen intermediate layers. However, our method, which quickly routes the signal to a single leaf feed-forward neural network, doesn't compare to deep networks. Now, let's talk about modular, mixture of experts, models. These models are essential for handling very large models. The simplest way to modularize large transformer models to reduce their inference cost is to divide their feed-forward layers into n blocks of neurons. Then, a controlling classifier is trained to decide which block to involve in the forward pass. This is typically done by training a wide softmax activated linear layer to produce a stochastic vector of mixture scores. These scores are then applied to the outputs per block to produce the final output. Several versions of this method have been proposed and tested across a variety of large models. We've compared fast feed-forward to mixture of expert networks in previous sections. To summarize, the mixture of experts approach reduces the layer inference width by a factor of n(k), where k is the number of best scoring blocks to engage in inference. However, it requires time proportional to n to select the k blocks and often relies on controlled randomization to avoid favoring only a few experts. This remains true even when multiple layers of expert mixers are introduced. On the other hand, a fast feed-forward network of depth d, where d is the base 2 logarithm of n, reduces the inference by a factor of n and only requires time proportional to d, or the base 2 logarithm of n, to decide which leaf to use. However, to compensate for having only one leaf to make the decision, the leaves of the fast feed-forward layer might need to be slightly wider than the blocks of the corresponding mixture of experts layer. Section Summary. Modified designs for MLP and CNN models have been proposed to allow for partial execution, where methods such as learning policy distributions or controlling neural components decide which blocks of layer neurons to execute during the forward pass. In comparison, fast feed-forward networks conceal the learning of leaf regions and come in an inference-ready form once trained, requiring no adjustment when included as part of transformers. On the other hand, modular, mixture of experts, models reduce the inference cost by subdividing feed-forward layers into blocks of neurons and training a controlling classifier to choose which block to involve in the forward pass, but this method requires more time for block selection and often relies on controlled randomization. In direct comparison, a fast feed-forward network reduces inference by a factor of n and requires only O log n time to decide which leaf to use. Section: Regionalization. The benefits of regionalization. The benefits of regionalization. One of the key benefits that sets FFF apart from similar work is its ability to directly link parts of the network used in the decision-making process to specific, identifiable areas within the input data. This unique feature can be used to prevent severe memory loss when making changes to models and to drastically cut down on the amount of data needed for replay by using the learned division of the input data to split the training data.